Thank you for coming down to IEEE here at UC Irvine. My name is Melvin, and we have a group of undergraduate research students. Our little project dates back 8 years to 2012, and back then we were essentially just trying to differentiate a cell line and just get it to beat. But now we're trying to innovate new and efficient stem cell therapies. And today we have two proposed products: the the cardiac patch and the cardio thread. Now, the cardiac patch is engineered to be a transferable patch for those suffering from myocardial infarctions. And the cardio thread is an alternative to just plain suture, as our cardio thread has stem cells embedded in it to promote regeneration post-surgeries, surgeries such as heart valve replacement. And in general, our project revolves around this cardiogenesis model because we understand the sort of prevalence that heart disease has in the world. So I'll pass it off to Brandon.
Right, so as Melvin said, our project stems from an increased urgency to address cardiac health in the world. So according to the Centers for Disease Control and Prevention, cardiovascular disease is the leading cause of mortality worldwide. It is a disease that claims 6.2 million Americans' lives over the course of a year. Heart tissue does not efficiently generate new cardiac cells with current therapies, and so the demand for heart repair therapies that are novel and efficient is evident. And so our project, we hope, will introduce a more cost-effective and efficient method for stem cell-mediated heart repair. And so we also want to develop it into a teachable laboratory paradigm that could teach students the fundamentals of stem cell therapy. And so in the past, we've been able to grow cells on surgical thread, and we were able to initiate contractile movement, and we also were able to manipulate the...
Just to pause you right there, I would like to show a video of proof that we've been able to add stem cells to sutures and have them beat. If only it would open. I guess it would. Oh, there you go. So if one could look closely, they'd be able to see beading where the finger is pointing. I think it's better.
Wait for it.
Oh, hold on. Closer look, maybe. There we go. All right. Now, as Brandon was saying.
Right, so we were able to initiate contractile beading of cardiomyocytes on surgical thread, and we were also, in another experiment, able to manipulate the structure of the cardiomyocyte structure and suspend the cardiomyocytes over linear strands of surgical thread. And so here are the models that we use to differentiate the cells onto sutures, and this is essentially the material that we used, and it was the central part of our experimental process. And so the first model shows cells that can grow on sutures, and the second model showed that tissues can be separated and suspended on different strands. And so based on our ability to create cardiac tissue, we integrated computer-aided design technology to create what we called the D-block. And that was a design that was created for the purpose of holding the sutures in place, fitting into a 6-well petri dish, and attaching to a pacemaker that could encourage uniform beating of the cardiomyocytes. And so what we also decided to do was to explore the idea of a portable surgical kit, something that we could use to efficiently line the suture with cardiomyocytes and do it in as expeditious way as possible. And so those components of the surgical kit include the assembler, weaver, and pacemaker, things that are just introduced on the screen here, but will be further discussed as the presentation goes on. And so the last part of my segment is sterility, which is basically the most essential asset of the success of our project. We wanted to ensure that every step of the process of generating cardiothread, which starts at culturing the cells and ends ultimately with creating the cardiothread, is done in as sterile a fashion as possible. So we would spray all the tools and all the equipment that we used in the fume hood with 70% ethanol. And because we have a goal to take a skin graft and take a patient's cells at bedside to create a more efficient method for this cardiothread generation, that's another aspect of sterility that we took into consideration, mostly because 2 layers of the skin are going to be extracted from the patient's skin, or from the patient's body, and so sterility could compromise the skin graft and the risk of infection in the patient is increased. And so Melvin will continue on with discussion of the weaver.
And so to start off the surgical kit, we have the weaver. And as Brandon was saying, once we have the patient's cells, we have to create a thread for those cells to grow on. And in this weaver model, it takes suture strands coated with transcription factors and weaves them into a custom thread. And the model on the right, you can see that the suture strands will be loaded at the bottom of the model and will be threaded towards the top. So it will be a parallel fashion upwards to create the new thread. And in general, this opens possibilities for not just cardio thread, but any sort of tissue, as stem cells will be able to differentiate into pretty much any tissue with transcription factors. And 2 big points about this whole model is that it has to be very cost effective, and we try to make the entire surgical model 3D printable. So once the suture is made, it is loaded onto a needle, and then it is taken to what we call the cardiac assembler. Now, Jasmine will introduce.
As Melvin said, most technology is capable of being 3D printed, which led us to develop the cardiac assembler to help us add stem cells to the thread produced from the weaver. We start with the weaver, we wrap it into the spool, and then it's taken to the cardiac assembler. Once this is prepared,
So once the suture comes from the weaver, we load it onto the spool model. And here's a little diagram of how that spool model goes into essentially one of the main parts of the cardiac assembly.
Once the suture is ready, it's able to move through the wheels by the knobs. The design of the knobs were caused to create tension and one-way turning. The mechanism of the gear also helps the suture to move in a constant pace. Once the suture is ready, we dip it into 4 wells, which contains, the first well contains gelatin, which is the fundamental substrate, elastic substrate that helps the cells form into cardiac tissues. Then the second well holds cells. In order for the cells to keep in one place, we use thrombin fibrinogen, which forms fibrin, which has helped keep it in one place. The fibrin also acts as branches out, and it becomes the path for the cells. And then prior to this, we also had this first prototype, which the vision was to pull out the sutures by hands and dip it into each well. It became really messy. So then we had a second prototype as well, and that one was also messy because we had to rotate each section and dip it. So the final product we have is the cardiac assembler, which is the location of the spool with reagents and transcription factors.
Right. And one last thing that I'd like to touch up on is that once the thread is loaded onto the spool, you're able to sort of fix it under these wheels here, and it will attach to what will then be cultivated in vitro. And it's this cardio thread spool. So we have like a little scabbard to hold the needle as it wraps and goes under the cardiac assembly.
So once the spool goes through the cardiac assembler, it is taken off and placed in a 6-well petri dish, and then it is cultivated for 2 weeks, and it is treated for 2 weeks at 5% carbon dioxide, 37 degrees, and it is treated with media 2 times a week. And the stem cells differentiate into cardiomyocytes through the media, which consists of alpha minimal essential medium supplemented with 10% fetal bovine serum, 1% pyruvate, 1% L-glutamine, 1% penicillin streptomycin, 1% basal medium eagle vitamins concentrate, 3% Bloom 75 gelatin, and 1% dimethyl sulfoxide. So the spool was, designed with multiple holes throughout the model to allow the media to seep through and thoroughly coat the sutures. And there are also holes on opposite ends to allow for the suture to span across so that we can monitor the progress of the cells. And once the stem cells have differentiated into cardiomyocytes, the spool is connected to a custom pacemaker, which will shock the cells to promote a synchronized beating and more uniform formation of the cells. And then the spool is equipped with guideposts on opposite ends to deliver a charge to the cells. And then the beading suture is ready for transplantation. And then in addition to the spool, we have the D model, which was designed so that sutures could be threaded through to create a block of tissue. And there are arches on opposite ends to uphold pieces of meat to see how the cells from the tissue will respond. And then on the side of the D model, there's a cutout to improve the process of changing out the media so that it does not disrupt the block of tissue. And it accompanied with the D model is a 3D printed lid that covers the petri dish that houses the model, and the lid is connected to a pacemaker that has platinum wires that will drop down to touch the model, which will shock the block of tissue. And now Kamille will talk about the application of the product.
So in modern surgery, suturing attempts to preserve the functionality and strength of the specific. So the use of cardio thread as opposed to normal sutures will possibly promote the robust cell regeneration around the surgical site. An application of cardio thread can be seen in heart valve repair and replacement, in which sutures attach synthetic or pig heart tissue to the pre-existing tissue. Now with our, next slide. Oh, that. With our cultivated cardiac tissue from the D model, it is used for larger scale damaged tissue as seen from myocardial infarction. This tissue block could possibly more effectively promote both attachment to the pre-existing heart tissue and the regeneration of new tissue post-surgery and for the long term. One of the most common abnormalities found in babies, congenital heart defects.
So what Kamille is trying to say is that the congenital heart defects found in babies, what we're trying to do to help counteract the defects is by using this cardiac patch to repair the sort of the atrial septal defect or any holes in the heart that any holes in the heart that the baby may have. And also another application would be using allogenic stem cells. So stem cells that come from any patient at any time to create more of a time-effective procedure. And finally, we have the robotic surgery application that we have made both the spool and the D model able to be used by like surgical robots such as the Da Vinci. And finally, we have our future directions. So afterwards, we would like to produce sort of a full-scale model of the CardioThread surgical kit. And we would also like to not only design both the spool and the D model to be compatible with Da Vinci robots, we would like to design the entire surgical kit to be compatible with robotic surgery. And finally, in the near future, we would like to apply our products in an animal model. And thank you for listening.
Thank you very much. Any questions, comments, or suggestions? First, this. 1 second.
Okay, questions. I'm sorry, I have trouble following. The D unit is a patch, right? And
Yes.
You're talking about a thread.
Yeah.
Okay, so question one, why wouldn't you use skin instead of, for example, circulating mesenchymal stem cells, which are easier to acquire and grow? Number one. Number two, instead of putting sutures on the thread, which I'm presuming what you're trying to do is facilitate healing by using the stem cells on the suture.
Right.
But if you're suturing graft anyways, there are already stem cells there. So if you had trophic factors on the suture that would promote the migration of those cells, yet you get the same point. If you were going to sew in a valve, for example, though, what about putting the stem cells on the valve itself instead of on the suture? Again, using the trophic factors on the suture to pull it in.
For the first point, we just decided to use a skin graft model. I'm not too experienced with that sort of obtaining that stem cell from patients, that method that you talked about. And as for the second point, we were hoping to use the CardioThread in just about any sort of practical surgery. And in regards of creating the whole like valve out of this cardiac patch, that'd be a great future direction, absolutely, yeah.
Thank you.
Any other question, comments, suggestion? Yeah, go ahead.
Question, when you put this on the thread, are you changing the strength of the thread and the size of how large it is? Where you have the thread, you showed that you had a yarn and you're putting on. How does this compare with existing sutures that are used? And is it larger, is it stronger, or?
No, it pretty much uses the same method to create the sutures. So most sutures are actually already threaded. But it doesn't change the thickness or anything. It's just a regular suture, just with coating in the inside, with transcription factors in the inside.
Any other question, comments? Any comments about, because you refer as application to basically blue babies, yes? That have problems with septal wall.
Right.
And that's, of course, when we talk about babies, that's very small dimension, yeah? When you show all these other things, yes, that's, different magnitudes. You know, how can you clarify to everybody how this fits together when it comes basically, very miniature patient?
A congenital heart defect is one of the most common defects in babies.
Yeah, blue babies.
One in about 2,000 babies.
Yeah, no, I understand, but basically it's, completely different dimension that adult human has. Yes?
Yeah, adult human heart to a baby's heart.
It's much larger, yeah?
I believe we'd be able to resize the cardiac patch and the cardiac patch to fit a smaller model. And that's what we're going to try to do for mouse, for the mouse trials.
How do you get that question?
He just, I'm not sure.
Any other question, comments, wishes? Any? Why everybody so quiet? What happened? Eh? Anyway, this was very suspicious. That's a group of people, they're very quiet. We reported, yeah. Anyway, there are no questions, yeah, thank you very much.